now for the math part to see if our physics in our game is matching up with what we'd expect in the real world. So we have this nice little kinematics equation here, and what you'll notice is that this equation does not actually appear in the code. We're just using this equation because this is what we'd expect in real life for it to happen. The code is actually just saying, hey, this is the time as far as it took for my spaceship to fall down to the ground. So using the math to see if our game is actually using the gravity correctly and physically accurately, we can go ahead and plug in the terms that we have. So our final position was actually 0, so we can go ahead and put that to 0, and because we're reaching the bottom of the screen when we land. And then our initial velocity is 0, so that whole term goes to 0 because we started out at rest. So now if we rewrite this equation with what we know, we get that 0 equals 250 meters, which was our initial position halfway in the middle of the screen, plus 1/2 times our a sub y, which is equal to negative g because our gravity is affecting our velocity in the downward position. So it's going to be that negative 1.63 times meters per second squared times t squared, which is what we're going to try and find is our time. So then if we go ahead and add this nice acceleration term over, then we get 1/2 times 1.63 meters per second squared times t squared equal to our 250 meters. So as Joe's writing that out here, then we're going to just do some algebra and multiply both sides by 2 so that we get 1.63 meters per second squared times t squared equal to 500 meters, which Joe prematurely actually put in there. That was 250 before. He's a step ahead. So now we have that 500 meters, and we're going to go ahead and divide both sides by 1.63 so that we get t squared is equal to 500 meters divided by 1.63 meters per second squared, which those meters would actually cancel out, so we get seconds squared. We need just regular seconds. So we're going to end up square rooting both sides to get t equals, and we put it in our calculators, it actually equals about 17.51. If you don't believe me, go ahead and check your own calculator there. But we got 17.6 in the game, so why are these not the same? The computer program actually is breaking up that time into little increments, and it's just adding it all up together. So you're actually going to end up getting a little bit, more or less. It might be a little bit off from what we calculate ourselves. But it's close enough to the same that we can go ahead and approximate it and say that our physics in the game is actually pretty close to what we'd expect in real life. So it's a nice physically sound game. So let's go ahead and go back to the green screen for one last look about something fun and try to challenge Joe again to see if he can win this game.